Hello and welcome to another lab video to finish up the Chemistry 112 lab material for the spring semester of 2020. This week, we're doing experiment 9, equilibrium and thermodynamics. Our objectives for this experiment are to determine the solubility product constant, the change in Gibbs free energy, the change in enthalpy, and the change in entropy for the dissolution of calcium hydroxide in water. In other words, for this process described by this balanced chemical equation. Practically, we're going to determine KSP values, and then from those values, be able to either calculate or graphically determine the other values. So KSP is an equilibrium constant, and like all other equilibrium constants, it describes the extent to which this reaction occurs. But KSP is only true when we have an equilibrium, and we have an equilibrium with solubility when we have a saturated solution. In other words, we've added more than enough of the solid form of the calcium hydroxide to maximize, in other words, saturate the solvent with calcium hydroxide ions, the calcium ions, and the hydroxide ions. So if we're given KSP, we can use that number to calculate the concentration of calcium and or the concentration of hydroxide in a saturated solution. Or conversely, as we'll see in this lab, if we're provided a saturated solution, and if we're able to determine experimentally either the concentration of calcium ions in that solution or the concentration of hydroxide of ions in that solution, we'll be able to calculate KSP. Practically, we could do either, but just kind of building upon what we've been working on the last couple of labs, we're going to determine the concentration of hydroxide ions in this experiment. And we're going to do so using a strong acid, strong base titration method, where we'll carefully react a known quantity of a strong acid, hydrochloric acid, with an unknown hydroxide ion, strong base. Our titrated mixture will begin with a known volume of the filtrate of the saturated solution. So in other words, we're going to first filter our saturated solution to remove the solid form of the substance. In this way, we get a sort of a snapshot of what the concentrations of the calcium ions and hydroxide ions were in that saturated solution. To that known volume of filtrate, we're adding a known volume of deionized water and a few drops of pH indicator. Notice that in contrast to last week, where we recorded pH readings to determine how the chemistry is changing as the titration progressed, this week, we're just going to use a pH indicator. We're going to titrate with HCl until we reach that indicator's endpoint. The indicator's endpoint is going to tell us when to stop the titration. And if we choose the appropriate indicator, then that indicator's endpoint, where we stop, will be at least a good approximation of what we're really after, which is the equivalence point. We'll use this titration method to determine the KSP of calcium hydroxide at 3 different temperatures: room temperature, warm temperature, and a hot temperature. The approach we'll use is that we'll start with the volume of HCl required to reach the indicator endpoint. From the volume of HCl and the actual concentration of HCl, we'll be able to calculate the number of moles of HCl. From the number of moles of HCl and the stoichiometry of the titration equation, we'll be able to calculate moles of hydroxide. From the moles of hydroxide and the volume of filtrate that we used in the titration, we'll be able to calculate the concentration of hydroxide in that saturated solution. From the concentration of hydroxide ions and the stoichiometry of the dissolution equation, we'll be able to calculate the calcium ion concentration. And then with these 2 numbers, finally be able to calculate KSP. So practically, we'll have volume of HCl for each of these 3 different samples. From volume of HCl, we'll be able to calculate KSP at each of those 3 different samples, where the only difference is the temperature. From those respective KSP values at those 3 distinct temperatures, we'll then be able to calculate delta G at those 3 temperatures using this equation, where R is 8.314 joules per mole Kelvin, and T is our Kelvin temperature. This is another equation that most of us should be familiar with that relates the change in Gibbs free energy to the change in enthalpy, temperature, and change in entropy. This is the usual form of the equation, but we can rearrange it to what's somewhat a more convenient form of the equation, at least for our purposes. This is more convenient because this is in the form of a line, which says that if I'm able to, one way or the other, either calculate or determine the delta G for a particular process at various temperatures, I can then plot delta G versus temperature. This should give me a linear relationship, and the linear trend line's y-intercept will be equal to the delta H of that process, and the linear trend line's slope will be equal to the negative of the delta S of that process. The lab report for this experiment is different from most of the lab reports that we've done this semester, in that this is one of the two formal lab reports. In other words, a typed lab report, similar to what you did for experiment 3 with kinetics. In order to have a better idea of what the expectations are, you should see the specific rubric for this experiment, or more generically, the formal lab report guidelines that are in your lab manual. And this experiment does have a pre-lab assignment. And it's very important that you do this pre-lab assignment pre-lab. In other words, that you do the pre-lab assignment, you write the answers to the pre-lab assignment before you watch the demonstration video, and certainly before you actually do any calculations. Because part of that pre-lab assignment is ask you to make some predictions about what the results are going to be. For your lab report itself, you want to start with an objective motivation paragraph, basically the purpose of the lab. Make sure you also include some real-world applications of either generically equilibria and thermodynamics principles, or specifically calcium hydroxide dissolution process. You should be able to write a full and detailed procedures from what you can observe from the video. Make sure that's in paragraph form, and as always, use passive voice. The results and discussion section minimally should include a table of the raw relevant data and a plot of delta G versus temperature. But you should also include not just simply the table and the figure, but also a sentence or two about the meaning of that data, a short discussion of why someone care about that plot, or why someone care about that raw data. And then a conclusion section, and certainly make sure you minimally include answers to those conclusion questions we'll talk about in the next slide. And then finally, an appendix, we show one worked out example of every unique calculation. And these can either be typed into the report directly, or if you want to do it by hand, you can certainly do so, but take a legible picture or scan it and then include that appendix as part of your lab report. When you're finished, then make sure you upload that lab report file and the pre-lab assignment using the link on Moodle. Make sure you do that before the grading deadline. Finally, our conclusion question. So what you minimally want to include in your conclusions is to first answer the question of the day. Second, then compare your pre-lab predictions for the sign of delta G and the sign of delta S to their respective experimental values, and a short discussion as to whether there was any differences. In other words, if you predicted one of the values be positive and experimentally turned out to be negative, or vice versa, why may that be the case? We use a pH indicator to tell us when to stop the titration. So describe what that pH indicator was, and come to some conclusions of whether or not it was a good choice. And finally, cite a published value for the room temperature KSP value of calcium hydroxide in water, and then compare that to your experimental value. And then end with a description of some experimental error or assumption that could reasonably explain why your experimental value was either too high or too low compared to your published value. And as always, in order to maximize your credit, make sure you're very specific in this as well as all other descriptions.